Welcome back to my optimization, sorry, and I'm going to do two more problems. This one is maximum area, but it's not a real life situation, it's on the coordinate plane. So here we have, we're looking for the maximum area of this rectangle that's underneath this curve right here. And this curve has this equation of, right here, x squared plus y squared equals 4. So if you'll, those of you that recognize that, that is the equation of a circle centered at the origin with a radius of 2. So we're going to see what's the largest rectangle that we can inscribe in that semicircle with a radius of 2. So this is a nice picture, and we're looking for the max area. Well, we normally do constraint and objective. In this problem, though, it's all labeled, the constraint is already in there. So let's look at see what we have. We have this semicircle here. So if the radius is 2, this is going to go over 2, up 2, over to the negative 2. So we know all these points here. We also know that this is another radii right here of 2. So here's this rectangle here. We don't know how long it's going to be, but we do know that it's going to be a negative x here, and we know it's going to be a positive x here. So the distance from here to here is going to be x, and the distance from 0 to here is going to be x. So the base of this rectangle, if you will, is 2x. We don't know exactly what that is, but we do know it's 2x. Now the height, let's figure out what the height would be. Well, the height right here, if we know that this point right here is on that semicircle, if I go over x and come up, I'm going to plug x into that formula. So if I know x here, so right here, if I plug in there and I know it's part of this, if I solve for y, this would turn to y squared, excuse me, is going to equal 4 minus x squared. And if I wanted to know what the y value would be, I'd take the square root of each one of them. That's where that came out to be. So I know the height of this rectangle is the square root of 4 minus x squared. All right. Now that's going to help us because we want to look for the max area. Well, the constraint is already in here. We know this length right here is going to be 2x, and the height is going to be radical 4 minus x squared. So we're going to say the area is going to be base times height. I'm just going to put the 2x in front, times the square root of 4 minus x squared. And I'm just going to rewrite it without the radical and without the parentheses. So you have 2x radical 4 minus x squared. All right. Now we want to figure out what the max area is going to be, so we have to do the first derivative. So that you recognize this. This is our f and this is our g. It's a product rule. So here's our f, here's our g. So f is going to be 2x. F prime is going to be 2. G is going to be, well, let's rewrite that. 4 minus x squared raised to the half. G prime is going to be 1/2 4 minus x squared raised to the negative 1/2 times the derivative of the inside, which is going to be negative 2x. So G prime, after I put all that together, because the 2's will cancel out and all that, we'll end up with G prime is going to be negative x all over, and I'm going to put that in the denominator, for the square root of 4 minus x squared. That's a 4, guys. Okay, so there's our G and our G prime. So let's do A prime right here. So A prime is going to be F prime G, so it's going to be 2 times whatever G is, and G is the square root, I guess I won't use the parentheses this time, 4 minus x squared, okay, plus FG prime. So FG prime, G prime is negative, so this is going to turn negative. It's going to be 2x squared, all right, all over radical 4 minus x squared. Now we're going to take that and put that equal to 0. Now when I get it like this, I'm going to move this whole term over on this side. It makes it a lot easier. So I have 2x squared, it's going to turn positive, over radical 4 minus x squared is going to equal 2 radical 4 minus x squared. Now what I'm going to do now is put this over 1 and let's cross multiply, and maybe we can get rid of that radical. So I have 2x squared is going to equal 2 times, now the radical's gone because a radical times a radical undoes it, so now it's just basically just 4 minus x squared. Okay, so these are going to equal, sorry, 2x squared equals that. And then I've got, okay, so this is 2x squared is going to equal 8 minus 2x squared. Let's continue down. So I want to get the x squareds on the same side, so I have 4x squared is going to equal 8. X squared is going to equal 2, and x equals plus or minus radical 2. Well, we're going to reject the negative because it doesn't make sense in this problem to have a negative height. Okay, so we're basically going to say x is the height of a radical 2. So if I come over here and if I put 2 times this, that means our answer, and we got to still check this, but for right now, the length is going to be 2 radical 2, because I just plugged a radical 2 here and here, by, and if I plug a radical 2 in there and square it, it's 2. 4 minus 2 is 2. So it looks like the height is just radical 2. So that looks like our answer. We need to check it with the first derivative test. So we're going to do the a prime bar, and radical 2 is here. So we're going to go to the left of radical 2, and again we're going to go to the form after the derivative has been taken. So you can either use this one right here, okay, look at it, you don't really want to put them equal to each other. So if I go to the left and if I use a 0, if you will, okay, it's going to come out to be positive. And if I use a 1 and plug a 1 in here, it's going to turn out to be negative. So this is a max area of this rectangle. And we did get the right answer. So here's our answer. 2 radical 2 by radical 2. Alright, we're going to do another problem. This one is a little bit more real life, and we're going to design a sign. And let's read what it says. It says, sign is to contain 50 square inches of printed material with 4-inch margins on the top and bottom and 2-inch margins on each side. What dimensions would use the least amount of paper? Okay, so we're looking for least amount. So when I see this, I know I'm trying to find a max or a min. In this case, it's going to be a min. So we know we have to do the first derivative test because it's extrema. So let's draw our picture. I like having a big picture of this. So we're going to draw this sign. And I don't know. It says paper, so it's, you know, it's got to be rectangular of some sort. Could be square, but we're not for sure. So this is supposed to contain 50. Sorry about all this. Let's make this look a little nicer too. It doesn't look very good. So let's make this look a little nicer. So I've got this sign here, and I'm supposed to have margins in here with 4-inch margins on the top and bottom and 2-inch on the side. Well, I'm going to kind of draw inside just because it's hard to draw, and I'll just label it different amount. So right inside here is our 50 inches of printed material. So here we're going to write all on the inside here. 4 inches on the top and bottom, so here's 4 inches of material here, a margin here and here, and on the side they said 2 inches. So let's label that. I know they'll look the same, but let's just pretend they're different. And what we're going to do is try to figure out how to make the dimensions with the least amount of paper, because we want to have 50 square inches of printed material. Well, first of all, I'm going to label these. So I'm going to call inside here X, okay, the printed material in the inside, and I'm going to call the printed material in the inside Y. So I just want you to realize, so here's all our printed materials on the inside. Let's label this, okay? So the X width I'm talking about is the printed material. It's not, the margins are not included, and the Y that I chose is the printed material. It's not with the margins included. That's important. So if I was going to do my constraint here that they gave us, the only well, they told us the margins, but we've labeled that in there, but the constraint is the printed material has to be 50 square inches. So I can say X times Y equals 50. That's my constraint. And let's go ahead and solve for Y right off the bat. So I have, it's 50 over X, because I know I'm going to substitute this in my objective. My objective equation in this case is I want to find the dimensions of the paper with least amount of paper. So here we use an area equation right here. This xy equals 50 was an area of equation, and so is our objective is going to be an area equation, but now we're going to use the whole side. So let me change the color here so you see what I'm talking about. The whole paper, the area, we're going to look at this, dimension and this dimension right here. So I'm going to come down right here. Okay? Now, what are the length of those sides? Well, I know the length of the outside of the paper is going to be x plus those two margins, x plus 4, and the y of the outside of our paper is going to be y plus those two margins, it's going to be y plus 8. Alright, so the area of the paper, according to how I labeled it, is x plus 4 times y plus 8. Now before I go through and multiply all this and have y's in there, I'm going to substitute this y right here into this spot right here, so that I'll have my objective all in x's. So if x plus 4 times 50 over x plus 8, and then I'm going to go through and I'm going to do the distributive property. So when I do x times 50 over x, that's just a plain old 50, plus x times 8 is plus 8x. Then we're going to do 4 times that, so it's going to be plus 200 over x. And then 4 times the 8 is plus 32. And then I'm going to combine the 32 and the 50, so I have the area is really going to be 82 plus 8x plus 200, and I'm going to rewrite it to the negative first power, because I know I've got to do the derivative of this. So now a prime is going to be, well, the derivative of 82 is 0, the derivative of 8x is 8, minus 200x to the negative 2, and we're going to put that equals 0. I'm going to rewrite that as x equals, I'm going to move this over here and rewrite it as 200 over x squared. Then I'm going to cross multiply over 1. 8x squared equals 200. X squared equals 25. Square root, square root. Now I know it's going to be plus and minus 5, but we're going to just say 5 because we're looking at the length of paper. So now I believe that right here, this dimension is going to be 5, and this dimension is going to be 9 on the outside. It's 5 on the inside. Now I want to find what the y is, so I'm going to plug the 5 in here. It's 50 divided by 5, or the y is going to be 10. So it's 10 here, and this is 18 on the outside. So they want to know the dimensions of the paper. So the dimensions of the actual piece of paper, not the printed area, the dimensions of the paper is going to be 9 by 9 inches. I should put the unit right there, sorry. 9 inches by 18 inches is what I think the dimensions are. But again, we have to test it to make sure this is the minimum amount of paper. So we're going to do a bar here, and we're going to do it as a prime bar to make sure that our 5 is really a minimum. So I'm going to go back up here and find where I can do my derivative. So it's right here. So if I plug into the left of 5, we'll say 1, you're going to get a negative. If I plug a 6 or more in there, it's going to turn out positive. So this is a minimum, so we're right. This is our answer. So there's 2 more problems that we got done for optimization.